Morning, students. Today we go to a new chapter, which is frequency domain analysis of BJT amplifier. I've already analyzed the amplifier in time domain. That means its voltage gain, current gain, input impedance, output impedance, and so many things. But frequency domain analysis, we have touched upon a little bit here and there, but we have not completely done the analytical investigation. Frequency domain analysis particularly means how the amplifier will act, rather, what will be its gain in very different frequencies, right? That is frequency domain analysis. And what parameters of the transistor determines that frequency domain performance. Start with performance at low frequency. Low frequency means less than 1 kilohertz or less than 500 hertz, sometime something at there. And here we have a common-emitter amplifier. This picture we have seen many times, and this is its Bode plot or frequency versus gain plot. This also I have shown you with simulation, with much software simulation. We have seen that at a certain frequency range, which of course is a very long range, the gain of the amplifier is more or less flat, that means fixed. But at very low frequency, its gain starts dropping and it becomes zero. Gain becomes zero at DC, that means zero frequency. Also at higher end, it starts dropping and finally it becomes zero. Now, we have defined 3 dB bandwidth, we call it. We have measured it, you remember, if this gain is, say, 100 dB, midpoint gain is 100 dB, then less than 100, that is 3 dB less than 100, that means at 77 dB, the two frequencies, they are called lower cutoff frequencies and upper cutoff frequencies. And for practical purposes, the working frequency range is taken to be from FL to FH, right? And by your arithmetic, you should remember that 3 dB drop means the gain becomes midpoint gain divided by √2. If the midpoint gain is 100 and that is divided by √2, that gain is minus 3 dB gain. So today we shall analyze about this low frequency part. That means what makes this drop at this low frequency and how we can control this frequency. Suppose you are using this amplifier for a music where very low frequency, that means the bus voices are also important. Say you want to use it right from 100 hertz, let us say. Say you want lower cutoff to be 100 hertz. Then what we should do? That's what we are going to analyze today. First, the low cutoff frequency is mostly determined by this emitter bypass capacitor. This I have shown you while doing multi-sim simulation of this amplifier. It is mostly determined by emitter bypass capacitor. And also, you have learned, I think you have learned in your school also, that in any RC combination, any RC circuit, the minus 3 dB point is given by omega C, that means omega cutoff point, which is equal to 2 pi FC is 1 by RC. Omega C is given by 1 by RC. I do not want to repeat that simple arithmetic once again. we take it that 2 pi fc is equal to 1 by rc. So here, the lower cutoff of by CE or emitter bypass capacitor. So due to C, what will be omega L? Lower omega L is 1 by RC. 1 by C is here. And what is the resistance here? Resistance RE. And also another resistance is in parallel. That is, the signal is finding a path RB, and signal also finds a path HIE, which is transistor's internal base emitter junction resistance. This HIE plus RB, and that HIE RB on the base side, when reflected to the emitter side, the value has to be divided by HFE. So this is the parallel combination, and which is multiplied by capacitor so that it makes 1 by RC. It is not necessary at this moment to go into further deduction, just to show you that HIE, you cannot do anything. Once you select the transistor, it is selected. HFE also, you cannot do anything. But RE and RB, these resistances are your selection. So once you have selected RE and RB, you know what is the value of omega L. So on the reverse way, if you want a particular omega L, then you determine emitter bypass capacitor's value of CE. So this is the first step. You should determine CE so that your cutoff frequency is your desired FL or higher, maybe. This is the first step. Second step. Now let's go to the second step. Now, due to this input coupling capacitor CI, there is also a cutoff created. So what is the resistance here is RB, and in parallel with RE, when reflected on the base side, RE is multiplied by HFE. So RB and REHFE are in parallel, and the capacitance is CI. Right? Once again, here, what you can do, so due to CO, sorry, there is something wrong. It should not be CO, this is CI. Omega L is equal to 1 by, and due to CO, sorry, I got a little mixed up. Due to CI, omega L is this. And due to CO, there is an output coupling capacitor. So far as the output coupling capacitor is concerned, there are two resistances in parallel. RC, for AC signal, it's shorted to common here, and RL is connected to common here. So here, omega L due to output coupling capacitor is 1 upon RCRN in parallel and CO, right? So I repeat once again. Due to emitter bypass capacitor, omega L is given by this. Due to input coupling capacitor, omega L given by this. Output coupling capacitor, omega L is given by this. So you have 3 omega L's, which is the correct value. The method, as I told you, you first determine C, because this plays the most predominant role. You first determine C, and once you have determined CE, then determine CI and CO using this formula, so that omega L for CI and omega L for CO is less than FL. I have got this point. This lower cutoff frequency has been obtained. CO has been decided. Once CO has been decided, then determine Ci so that omega L due to Ci is lower and omega L due to CO is also lower. So if they are on the lower side, you don't bother about this. So main predominant factor will be played by CE, and that should be meet this criteria of lower cutoff frequency, right? So this is how this particular common emitter amplifier, which is the most commonly used amplifier, works as a lower frequency. At lower frequency, the gain gradually drops, and minus 3 dB frequency can be determined by this, and minus 3 dB frequency can be determined by properly selecting the emitter bypass capacity. This is so easy. But mind it, at higher frequency also, the drops. Although this higher frequency is very much outside the audio range, this is of the order of megahertz and sometimes in terms of gigahertz. So normally you don't have to bother if you are in the audio frequency, audio amplifier range, right? But still, since you are a student, you should know what really plays part, what really decides the upper frequency. See, none of these capacitors decide the upper frequency. Then who decides the upper frequency? This upper frequency cutoff is a completely different ballgame. So we go to that performance at high frequency. This analysis appears to be a little bit cumbersome, and I feel you need not memorize everything, but just try to understand how we analyze and finally remember the final outcome at a high frequency. At high frequency, what happens? Base emitter and base collector junctions have inherent junction capacitances. This you have learnt in your device classes, possibly in earlier semesters. Base emitter and base collector junctions both have, base emitter junction has the diffusion capacitance, base collector junction has the depletion capacitance, but these capacitances, their typical values are in picofarad. Base emitter value is 50 picofarad to 5 nanofarad, and base collector is 1 picofarad to 30 picofarad. That means they are very, very small capacitances. That is why in audio frequency analysis, we totally ignored them. We at all didn't talk about them. But if your operating frequency, signal frequency is very high, their values are so small and they are ignored at low frequency. But at high signal frequency, offer a reasonable reactance and affect the amplifier's frequency domain performance. So we need to take a completely different internals of a BJT. Mind it, these capacitance are internal, intrinsic properties of the BJT. When the BJT was manufactured, then these capacitances were there inside. We cannot take them out. Today we are going to learn how these capacitances affect the amplifier's performance. First, this is the hybrid pi equivalent model of a voltage input common emitter BJT configuration. In our last slide, we showed this voltage input common emitter BJT amplifier. Here, the hybrid pi model. How? This is the BJT. This is only the transistor. This is only the transistor. Now, I will explain what are all these things in a transistor. Many of these we did not consider at all so far. What are all these things? B is the base junction base emitter junction. That is, if you drill into the transistor, there is a junction, that junction. And this B is the base terminal. That means the terminal that you can see from outside. And there is a resistance between B, the terminal, and the junction. Even the terminal pin also has a resistance. RBB dash, resistance between the junction and the terminal. And its value ranges from 10 to 50 ohm. And this small value, so far we have ignored. So far, we took the junction at the terminal to be same thing. Now we will not ignore. Now, there is another resistance. This is the junction resistance that so far we have talked about. This is the base emitter junction resistance. RB-E is equivalent to the junction resistance HIE, which you have learned, which value is I've given in the bracket. It is 25 HFE by when IE in milliampere, that we have been considering so far. And this is much larger than RBB dash in AT. That means this resistance is much larger than this resistance. So we considered this right from the beginning, but we ignored this. Next, this capacitance is the base emitter junction capacitance, diffusion capacitance at the base emitter junction, which we have ignored so far. That is CB-E, right? And there is another capacitor. This is the most dangerous capacitor. That is the depletion capacitance between the collector and base, CB-C. And this collector base is always reverse biased. And that is why the value of this capacitor is quite considerable. It's not negligible. This is the capacitance between the base junction and the collector junction, right? And is the voltage across the base emitter junction. This positive negative polarities are conventional polarities. Actual value can be reversed. That will come out when we do the arithmetical deductions. GM is the base emitter signal, base emitter voltage to current ratio. That means so far we normally talked about alpha or beta. That is the ratio of collector current to base current. But today's deduction will be easier if we start with collector current to base emitter voltage ratio, and we have just given it a name GM. So this collector current is GM multiplied by VBE. So far we had been always writing the collector current is alpha times or beta times the base emitter voltage. Now we write the collector current is equal to GM times the base emitter voltage, right? The GM is a new introduction here, but finally it will go out of the deduction, but it will make the deduction comfortable. Next, this is the common-emitter amplifier again. Now, this is the transistor. RBB, RB-E, VB, CB, GMBB, CC. I go back. I show you here. This is the transistor. RBB, CB-E, RBE, GMB. So this is the transistor. That means this BJT. And now we add the external components. This is the RB, right? This is I'll talk a little bit later. This is RC, collector current, collector resistance. This is RL, uh, resistance. This is the hybrid pi model of the total amplifier. The yellow part is a hybrid pi model of the transistor. This is the total amplifier. Here I have made a change. I have written here what is the change. Collector current is equal to HFE times VB dash E by RBE. This collector current is HFE times emitter current. I repeat once again. Collector current is equal to beta times the emitter current. This we have done right from the beginning. So HFE multiplied by what is the emitter current? Emitter current is VBE divided by RB dash E. This is the base current. I'm sorry, I have been telling you wrongly. IC is equal to beta IB or HFE multiplied by IB. That means base current, right? Now, what is the base current? Look at this VBE. This base current IB dash is VBE divided by RB. This is the current passing through this. So, HFE VB by IB. Now, this ratio HFE divided by RBE, this ratio, we give it a new name GM. Why? Because if I write a single term GM, then I don't have to repeatedly write this same ratio again and again. So it is GM VBE. So collector current is GM multiplied by this VBE emitter voltage. Also, these coupling capacitors, two of them, and the emitter bypass capacitor, we have considered them ideal because we have seen their role is in the lower frequency. So at higher frequency, we consider them they are ideal. They are creating total short circuit here, here, and here. So that is why these capacitors are not appearing here at all. Also, now I'll come to this. This voltage source Vs, signal source Vs, it has been replaced by its Norton equivalent, a current source in parallel with a source admittance, II and Ri. And you know what is the Norton equivalent, what is the value of this resistance, and this is the value of the current. So this whole amplifier is represented by this schematic circuit. After that, this is now simplified here. What is the simplified? Now I'll tell you, don't get threatened by this certain diagram. This diagram I have showed you, this is the perfect whole diagram. Now step by step we shall go on simplifying them. Finally will be left with a small diagram. So from here, what is the simplification we have done? RB, that means this resistance is much smaller than Ri is much higher than RB. Ri is much higher than RB. If Ri is much higher than RB, then Ri and RB in parallel, they make almost equal to RB. You know that. If Ri is much higher than RB, then their parallel combination is RB only. And you know the parallel admittance of any current source is always in terms of mega. Right? So this is RB. This is one simplification we have done. Another simplification we have done, RC and RL. Normally, RC is much higher than RL. So RC, RL in parallel will be almost equal to RL. So this is one step of simplification. We could draw a picture of all simplification in one step, but then understanding it would have been very difficult. So this is the first step of simplification. Next, what do you do? This register is really the, what to say, the root of all problem, this capacitor. Because capacitor is connecting the base side and the collector side. And if there is any element connecting the two sides, then it becomes very difficult. So, but there is a way, and that way you have learned in your network theory circuit, how to divide them into two parts. Look at capacitor, CB dash C. What is the potential on the left hand side? VBE. And what is the potential on the right hand side is VCE, collector emitter resistor, right? So this is no problem. This is correctly reflected here, you agree? If it is that, then it can be replaced by a two-port network. The same VBE here, VBE here on the left hand side. On the right hand side, there is a VCE and there is a capacitor. And there is a second part where on the left hand side VBE and right hand side is same capacitor C B dash C and here is C. So you agree that I have not done any magic or anything here. This is the same thing we have split into two parts, right? Once we have done that, then this is the splitting. We have done it, right? Then thing can be replaced by this thing. What? On the left hand side is CBC, VCE, VBE as it is. On the right hand side, this is a voltage source and a capacitor. Capacitor means some kind of impedance. Voltage source and an impedance in series can always be replaced by its Norton equivalent of a current source and admittance in parallel. What is the admittance in parallel? The same C, B, C, and what is the current? Now, what is the current through this? Current through this line is this voltage VBE divided by this impedance, and this impedance is omega C BC. So current is VB divided by 1 upon omega C BC, which is equal to CBC omega VBE. So this voltage source in series with an impedance has been simply replaced by a current source in parallel with a admittance. So this also you should agree. So this was our original diagram. Now only this part we have split into two parts here and then shifted it here. Then what do we do? Then this part we bring in here and this part we bring in here. Now look at this. This is, there is a current source, there is a impedance, right? Then there is this capacitance C B dash E is here. Now this capacitance has been divided by two parts. One part is here, C B dash C by VCE. That is C B dash C and supplied by VCE. And on the right hand side, this part, right? This is this one, and this capacitor C B dash C and this GMVBE was already there. Resistor RL was already there. One approximation we have added, that is, here it was RB, smaller BB, RBE. We have replaced the whole thing by RB dash E because this is only the resistor circuit. Capital RB dash E is equal to RBE in parallel with sum of these two resistors. So since this resistor, three resistors has been replaced by one resistor. I think you have no problem in agreeing to this. Resistors have been replaced by one resistor. This capacitor is already here. This capacitor Base collector junction capacitor has been split into two parts. Left hand part is this here, and the right hand part is this here. This current source GMVB is still there, and the load RL is still there. Have not done anything mischievous, so we have just replaced the circuit by its equivalent. Okay. Next, further, what do we do? This omega C B dash C, this is a current source, and GM V GM, this is a current. These two current sources are in opposite direction, right? And both are multiplication of VBE. VB, but omega C B dash C is always very small with respect to GM. So this current source has been removed. See, this current source is not there. And also, this impedance, this creates an impedance of 1 by omega C B dash C, and there is a parallel resistance RL. This impedance is always much, much higher than RL. So this has been removed, as if their combination of these two parallel is as good as RL. So we have just converted this one to this one. So actually what we are doing this conversion step by step, so that at each step you agree with the arguments. Now look at the output. From the output, what we find? VCE, the polarity positive upward, it is taken. VCE current multiplied by this resistance with a negative sign, because if the current flows in this direction, then this becomes positive, but our conventional polarity is positive upward towards the collected side. So it is minus GM RL VBE. That means output potential across the collector emitter is given by this equation, right? Next, in that case, what is the current through this capacitor? This current, this blue arrow that I am showing, because this current through this capacitor is it's supplied by this source VCE, whose value I have got here, right? So what is the current through this capacitor? Current through this capacitor is, this current is called current ICB dash C. That means this current is equal to, it has got this current, will have current is equal to this VC, its value is GMRLVBE, GMRLVBE. This is the current, and this is another current, there is a VBE. I repeat once again, this VBE potential is trying to drive a current in this direction. What is the value of this current? If this is the conventional direction of current, what is the value of this current? VBE, voltage divided by impedance. But impedance of a capacitor is 1 upon omega C. So it is VBE multiplied by omega C. This is VBE multiplied by j omega C. And there is another current. This source is trying to give a current. This source is trying to give, and this source is positive in this direction. So this source current should be taken in a negative direction. But already there is another negative sign. So this will be added. So this current is this source VCE. VCE has been replaced by this value and once again divided by the impedance. So what do we see? The current IBC through here is actually J omega CBC within bracket 1 plus GMRLVBE. So what we get here really? We get here This dependence of collector emitter voltage on the base emitter side we got rid of, because this is the collector emitter voltage, but it is appearing on the base emitter side. So it made our analysis very difficult. We got rid of. So this current is actually now only related to the base emitter voltage, right? So this resistor, this resistor, this capacitor now can be replaced by a capacitor of this entire value C, C B dash C multiplied by 1 plus GMRL, C B dash C multiplied by 1 by GMRL, and the same VB. I repeat once again, if this is the current and this is V, what appears? It appears that there is a resistance, that there is a capacitance which has a new value, and the value is CBC within bracket 1 plus GMRL. Now, what we have achieved after all this hard work is that base emitter side and collector emitter side is totally isolated. That makes the analysis very simpler. And this capacitance is called the Miller capacitance. Very often you face this question in your Viva, etc. What is Miller capacitance of a transistor? You cannot really recollect and remember all these equations. What you can recollect, Miller capacitance is if the base collector junction capacitance is reflected into the base emitter side, then this new value of capacitance, this is called Miller capacitance of the BJT. So now we have this circuit. This is the circuit. I repeated once again the same picture, right? Now, what is the combined impedance of all this? Now, you will find now the analysis will be very simpler because there is no connection between the left-hand side and the right-hand side, base side and collectors. Combined, if you find combined impedance of all this, I can find VB. Combined impedance of all this is RB dash E in parallel with, and these two capacitances in parallel makes this impedance, right? So, because two capacitances in parallel, their impedances, their equivalent capacitance is the sum of them. So CB dash E plus CM and omega 1 upon omega of that is the impedance of this part, which is in parallel with RB dash E. So this becomes, and parallel combination calculation, you know, it is RB dash E multiplied by this factor divided by RB dash E plus the same factor. And if both numerator and denominator multiply by omega within bracket CB dash E plus CM, then on the numerator you are left with only RB dash E, and the denominator it will be 1 plus omega RB dash E CB CM. So this is the total impedance here. So what is the current? Now this current and this voltage relation is easy. So what is VB? Is I, this current multiplied by this total impedance. This is the total impedance, I multiplied by this total impedance. From here, what do you get? I1 input current is equal to VBE multiplied by this whole factor, multiplied by this whole factor divided by RB. So this is the input current. And what is the output current? Output current was very easy right from the beginning. Output current is GMVB dash E, but their direction, conventional direction is opposite. So there is a negative sign. So now we can find the current gain. So current gain is output current by input current. Both have a factor of VB dash E. So it is minus GM RB dash E divided by this factor. 1 plus omega RB dash E CBE plus CM. So we have this current gain. We have almost reached the target. If this is the current gain, what is the magnitude of this current gain or mode of this current gain is GMRB dash E divided by whole under root 1 square 1 plus this thing square, right? Now, when when this factor omega RB dash E CB dash CM is much less than 1, when this is much less than 1, this is much less than 1, then your this gain becomes only GMRB dash E, only GMRB dash E mod magnitude. Don't ignore the negative sign. So this is the mid frequency gain, GMRB dash E. See, and as such, we could as such assume right from the beginning that this is the current gain. But we have done all this analysis to be sure that yes, this is the current gain. When this thing is equal to 1, this thing is equal to 1, right? Then this mode of current gain is GMRB dash E divided by root 2. Now, I told you at the beginning of today's lesson that when the gain becomes 1 upon root 2 times, that is the minus 3 dB frequency. So, upper cutoff frequency is actually this is equal to, this is omega equal to omega r etc. is equal to 1. So omega is 2 pi FL. So FL is FH. So FH equal to 1 upon 2 pi RB CB dash E plus CM. So what decides the upper cutoff frequency of my amplifier? One thing is RB dash E, that is the input side impedances or resistances, and CB dash E. CB dash E is the base emitter junction diffusion capacitance, and CM is the Miller capacitance, right? One thing I want to show, but now I cannot revert back to this. Here, it should be this whole under root. This should be 1 plus this thing square. So just make a square in your note, okay? So we have got upper frequency. We shall take only only 2 or 3 more minutes to discuss on this upper frequency. So this is the mid frequency gain and this is the upper frequency, right? Then we come to conclusion. So as I told in the beginning of today's lesson that you may not be able to remember all these deductions, but please do remember the conclusions that we are going to discuss now. Multiply these two, then RB' gets cancelled. So product of the gain and the upper cutoff frequency because GM upon 2 pi into this. So mind it, all these three factors are completely dependent upon the transistor's manufacturing. So this product is called the gain bandwidth product or GBW. If you look into any transistor manual, very often the GBW value is given, what is GBW? If somebody asks you in Viva, what is the gain bandwidth product? It is the mid-frequency gain multiplied by the upper cutoff frequency. The relevance of this GBW. This is the GBW. It has got three terms, GM, CB-E, CM. We shall see all of them separately. This is GM. GM is, we have seen earlier, HFE by RB-E. HFE of any particular transistor, a BJT is fixed. Once you have purchased, it's fixed. Or once you have manufactured, it's fixed. RB dash is the base emitter junction resistance of the transistor. It is also fixed after manufacturing. Then we have these two, CB dash E or CM. CB dash is the diffusion capacitance of the base emitter junction, which is fixed after the transistor has been manufactured. And there is CM. What is CM? Remember, CM is this. In this CM, within this CM, there are two terms. One is CB-C, which is a capacitance of the reverse bias base junction collector depletion region. That is also fixed once the transistor is manufactured. GM, we have already discussed. What is RL? Only RL is determined by the circuit designer. RL is the load resistance, right? That means once the load resistance is chosen, without the load, besides the load resistor, everything is fixed. So you cannot alter anything in the gain bandwidth product. And once you have used the transistor in an amplifier and you have decided the RL, then gain bandwidth product of that amplifier is fixed. You cannot do anything. Once you have decided the RL, then by doing other calculations, you can increase the gain. You will see its bandwidth has reduced. Upper cutoff frequency has reduced. If you try to increase the upper cutoff frequency, you will find automatically, finally, after all calculation, that its gain has reduced, right? So this is the relevance of the gain bandwidth product. Next day, we shall go in other aspects. So we finished our lesson today. Next lesson, we shall go into, how we have seen, we go to at the very beginning here. We go to at the very beginning here of today's lesson. There was a board plot diagram. This was the board plot diagram of one stage of amplifier. What happens to this diagram if you cascade another stage? Because that you do very often in an amplifier. In a amplifier in a sound box that you play in your music concerts, the amplifiers in one stage, it cannot give such a high amplification. There are many subsequent stages. And what happens when you add one stage after another stage? What happens to this gain board plot? That we shall discuss in our next lesson. Okay?